So now we'll move to the non-Newtonian aspects of blood. So we saw that how a Newtonian fluid was defined as something that follows shear stress is equals to dynamic viscosity times the strain rate or the velocity gradient. So it is not necessary that all fluids follow this formula, just like it is not necessary that the stress is equals to elastic modulus times strain in a solid. There can be non-Hookean solids which have a viscoelastic response. So similarly, in a fluid, the simplest fluid is a Newtonian fluid that follows this formula. But if it doesn't follow this formula, then at any given point in a non-Newtonian fluid, for example, we can select the point using different criteria, for example, at different strain rates. It might have an effective dynamic viscosity. So if you plot strain rate versus dynamic viscosity, it could change over the strain rate. So as the strain rate increases, the dynamic viscosity could decrease. Say the strain rate increases and the dynamic viscosity decreases. So the strain rate increases, usually there's more shear stress, and the viscosity decreases, then this could be termed shear thinning. Fluid is now flowing much more without stress as it increases in the gradient. Another thing that could happen is that as the strain rate increases, the dynamic viscosity could increase. This could be called shear thickening. We will learn in a bit that blood follows shear thinning. So shear thinning is what blood does, and we will look at why it does that. A Newtonian fluid, on the other hand, has constant dynamic viscosity as we change in strain rate or shear stress. So this could have been, we could have plotted it with respect to strain rate, or we could have plotted it with respect to shear stress tau, which is in pascals. So because of the relationship, tau is equals to mu effective times the strain rate. The strain rate is the change in velocity with respect to distance. So meter per second divided by meter, so you're left with per second. And shear stress is Newton per meter squared, which is pascals. And effective modulus, the effective modulus is Pascal second. So if this is Pascal second, this is per second, then the per second and second cancel and you're left with pascals. Instead of plotting the effective dynamic viscosity with respect to shear stress or strain rate, we can plot strain rate with respect to the shear stress. For Newtonian fluid, this is a straight line and the slope of the line. So if you take the slope of the line, then this is, so if this is 1, then this is mu effective, or just mu, because mu effective is constant, and this is Newtonian. For a shear thinning material, initially the mu effective is similar to Newtonian. So let's say it has a similar to Newtonian characteristic, but after a while, the change in shear stress, the shear stress is not as high as you would get for a Newtonian fluid. So it actually thins. So you have less shear stress as you increase in strain rate. So this is shear thinning. Shear stress is less, which means the mu effective, if you look at the slope here, dy dx, this mu effective is also lower than here. So here mu effective is higher, as we increase in strain rate, mu effective is getting lower. So this is a shear thinning phenomenon. Now it doesn't have to be like this, it can be like this. It's just concave down. So anything that's concave down, when you plot this shear versus the um, strain rate, and if it is concave down, that is shear thinning. So this is also shear thinning. Conversely, to get shear thickening, you would see that the curve is concave up. As you increase in strain rate, shear stress increases more than you would expect in a Newtonian fluid. So initially, the shear stress, so all these curves that are concave up are shear thickening material. So these are shear thickening. So over here, it's a little bit, let me draw that a little bit more properly. So initially the curve, the slope is smaller, and as you go higher along the curve for higher strain rates or shear stress, your slope is higher. And this is a mu effective is initially lower, mu effective initially lower. Over here, mu effective is higher.